Hi everybody, I hope this video finds you well. In today's video, we're going to be working through section 8.8 from your textbook, talking about an example of a differential equation with non-constant coefficients. So let's get into our definition here and then talk about the main idea for how we're going to approach this new class of differential equation. So, an nth order Cauchy-Euler differential equation is a linear differential equation of the form x to the n times y, the nth derivative of y, plus a1 x to the n minus 1 times the n minus 1 derivative of y, plus dot 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 all the way down to a n minus 1 x times y prime plus a n y equals 0. So a Cauchy-Euler differential equation is a very specific form of linear differential equation, similar to how a constant coefficient differential equation is a form of special linear differential equation. What's the defining sort of way to think about this Cauchy-Euler differential equation? Well, what you should sort of recognize is that it's constant coefficient, except that along with the constant coefficients a1 through an, you also have a factor of x to the same power as the order of the associated derivative. So notice that we have the nth derivative of y with x to the n. We have the n minus first power of x with the n minus first derivative of y. We have the first power of x with the first derivative of y, so on and so forth. So that's really the defining idea of a Cauchy-Euler differential equation. When working with a Cauchy-Euler differential equation, and the sort of main theoretical part of what we're going to be doing in this video is we're going to try to follow this main idea. We're going to try to show that a substitution of the form x equals e to the z will turn this into a constant coefficient differential equation. And once we've converted it into a constant coefficient differential equation, then we can solve it using our standard approach where we sort of look at the roots of the auxiliary polynomial and then undo the substitution to get solutions to the actual Cauchy-Euler differential equation. Now, we're going to prove in just a few minutes in general that this substitution, how this substitution sort of works and why it actually creates a constant coefficient differential equation. But before we do that, let's look at an example and actually just try to mess around with the substitution and see how this works. So we're going to try to find the general solution to this Cauchy-Euler differential equation. X squared times y double prime minus 4xy prime plus 6y equals 0. This is certainly Cauchy-Euler because you can see that the x squared is paired with the y double prime, the 4x is paired with the y prime, and you just have that 6y term. All right, so let's try this substitution. So what we're going to try to do is we're going to try this substitution here. X equals e to the z. Now, it might not be immediately apparent where this is going to come in, but we're going to see that it's going to involve some unpacking about the derivatives here. Now, I do want to also make another note. By saying x equals e to the z, that's also the same as saying z equals ln x, right? Those are saying the same sort of substitutions there. All right, so we've got substitutions to do here, but we have to keep in mind that we've got derivatives here. So before we do anything else with this substitution, let's sort of rewrite this in an expanded form. And what I mean by that is let's actually write out what these derivatives look like, making sure that we know what they're with respect to, especially since we're going to be changing variables. So keep in mind this differential equation is really x squared times the second derivative of y with respect to x minus 4x times the first derivative of y with respect to x plus 6y equals 0. All right, now we're going to think a little bit about how we can convert these derivatives into derivatives with respect to z, which is going to be our new independent variable. We're still going to keep y as our dependent variable, but we are going to change the independent variable here. So let's go ahead and see if we can do that. So what can we say about dy dx? Well, right now, we're thinking about y as a function of x. But let's think about y as a function of z, and then z as a function of x. Now, a very simple chain rule will tell us that dy dx then can be thought about as dy dz times dz dx. That's thinking about y as a function of z, and then z as a function of x. So this right here, that's just chain rule. All right, but let's see if we can say a little bit more about this, right? Now, we don't know what y is, so we can't really say much about dy dx or dy dz. But we can say something about dz dx, right? Z equals ln x. So we know dz dx is actually going to be 1 over x. So we can say that this is dy dx is equal to dy dz times 1 over x. Now, notice I could bring this 1 over x onto the other side, and I get a very interesting sort of relation here. X dy dx is equal to dy dz. Now, the reason that this is so interesting is that notice we have an x dy term right here. This term right there is going to be replaced by y's derivative with respect to our new variable z. Now, just to make things a little bit easier, we're going to let d represent, right? Normally that's our differential operator derivative of y with respect to x, but now we're going to treat it as our derivative with respect to z. So we're going to let this letter d, that operator, represent dy dz, the derivative of y with respect to z. So we've just gotten that dx times dy dx is equal to this operator d. All right, now that's going to tell us that this component right here is going to actually become reduced as not minus 4x dy dx, but as minus 4d, because that x dy dx is equivalent to the derivative with respect to our new independent variable z. Now we need to think about this guy. So to do that, we're going to need to think about the second derivative here. So let's think about the second derivative. So the second derivative of y with respect to x, well, what can we say about that? Well, we certainly know that that's the derivative with respect to x of dy dx. I mean, that's how you get the second derivative. You repeat the derivative on the derivative. So that tells us that the second derivative of y with respect to x is really the derivative with respect to x. And what do we know about dy dx? Well, we know it can be written using chain rule like that. So dy dz times dz dx. Okay, and of course, we know that that is actually equivalent to 1 over x, so let's just pop that in there. So we actually can say that this is the derivative with respect to x of dy dz times 1 over x. Okay, now let's distribute this derivative over this product using product rule. So we can say the second derivative of y with respect to x is actually, well, we're going to have to take the derivative here and then apply the derivative here. So that'll give us dd dx of dy dz times 1 over x plus dy dz, and then we'll apply this dd dx of 1 over x. Well, we know how to do that one. That's just going to be negative 1 over x squared. So the only thing that's really sort of complicated in this is what happens when we take the derivative with respect to x of the derivative of y with respect to z. Well, what's going to happen here is it's going to be a chain rule. This is y as a function of z. So when we take the derivative of with respect to x, it's going to be the derivative of that with respect to z times the derivative of z with respect to x. So that's going to give us that this is actually going to be the second derivative of y with respect to z. That's doing that derivative with respect to z. And then we get an additional factor of the derivative of z with respect to x. This right here, again, is the chain rule. Then, of course, we have times 1 over x, and then we have plus this dy dz, and then our negative 1 over x squared. All right, well, that's pretty much a tremendous mess here, but let's do a little bit of simplification. Let's multiply both sides by x squared. So we would get x squared, and, well, actually, let's do one thing before that. We can actually clean up one more piece here, right? The other piece that we should be able to clean up, right, is right here, that dz dx. We know that anytime we see that dz dx, since z equals ln x, we can put that in as a 1 over x, and we can make this equal to the second derivative of y with respect to z times 1 over x times 1 over x, just replacing this guy with a 1 over x, since we know that's what it is, and dy dz negative 1 over x squared. Okay, let's multiply both sides of this by x squared, and we're going to get x squared times the second derivative of y with respect to x is going to be the second derivative of y with respect to z minus the first derivative of y with respect to z. Now, what's interesting about that? Well, this guy right here is going to be that first component of our differential equation. And notice that this here, in terms of that operator notation, would now be x squared d squared y dx is actually going to be d squared minus d. So what we just figured out is that we can replace this component of our differential equation with d squared minus d. We can replace this component with d itself, and then we'll have a differential equation where y is still the dependent variable, but now z is our independent variable. So let's go ahead and actually look at what that's going to look like here. So we originally had this as our differential equation. I'm just going to go ahead and take the moment to rewrite it. Minus 4x dy dx, and then what else do we have? Plus 6y equals 0. Now, like we said, we just figured out that x squared times the second derivative of y with respect to x is equal to d squared minus d, and we figured out that x dy dx was equal to just the first derivative of y with respect to z. So let's plug those in. This is going to become d squared minus d minus 4, and then this entire x dy dx is going to become d, so we get minus 4d, plus that 6y equals 0. Right? So if we think about what that looks like then, we can simplify that a little bit, and we should be able to see that that's going to become d squared minus 5d plus 6 of y equals 0. Technically, both of these guys are of y as well. I just didn't have that notation in there. We could have said that both of these guys actually should have had of y here, but it's just notation. So there we go. That's what we actually have as our differential equation. Can we solve this? Well, it should be pretty easy to do so. We can factor that. D minus 2, D minus 3 of y equals 0. So the roots are r equals 2 and r equals 3. This guy has multiplicity 1. This guy has multiplicity 1. So what do the solutions look like here? Well, we'd get y equals c1 e. Since this is a root of 2, we would normally get 2x. But of course, x is not our independent variable here. We'd get e to the 2z. And then we get plus c2 e to the 3z. So there we go. There are our solutions. It's just not in the correct original variable. But now we can use our substitution, right? Remember that our substitution is, we can think about z as ln x, or if you prefer, you can think about x as e to the z. Now, either way is going to simplify a little bit. So let's just actually go ahead and say z equals ln x. So this is going to become c1 e to the 2 ln x plus c2 e to the 3 ln x. But what happens here? Well, these are going to cancel and give us x squared, and then cancel and give us x cubed. So we see that our solutions here are c1x squared plus c2x cubed. So those will be our solutions. That'll be our general solution to that Cauchy-Euler differential equation. So let's quickly recap what we did here before we talk about how we're going to do this in general. So when we look at a Cauchy-Euler differential equation, we identify it by seeing these polynomial pieces multiplied with their corresponding derivative of y. The idea that we're going to be using here is that we use the substitution of x equals e to the z, with the hopes that that'll turn it into a constant coefficient differential equation. We saw that doing that substitution, that x dy dx, which is going to be one of those pieces we always have in a Cauchy-Euler, is equivalent to the derivative of y with respect to this new independent variable z. Then we did a tremendous amount of more work to figure out that the x squared times the second derivative of y with respect to the original independent variable x was d squared minus d, again with d representing the derivative now with respect to z. So this introduced a little bit of a difference here. When we plug that in, what was originally x squared, second derivative, minus 4x, first derivative, plus 6y equals 0, actually became d squared minus 5d plus 6 times of y equals 0. And then we were able to factor that, look at the general solutions that are in terms of z, and then undo those substitutions to get our solutions in terms of x. Now, I will let you guys know that in the second order case, your book does a little bit of a different derivation, sort of with a guess and check, sort of speculating that maybe the solutions will look like this, and then seeing how to actually determine that they would be x squared and x cubed. I don't really like that because it doesn't work so well for higher order ones, and we're going to just be looking at how to use this substitution in general. But notice that it shouldn't be a surprise that when you're solving these Cauchy-Euler equations, you're often going to see powers of x, because when you do this substitution with z equals ln x, any exponential term you originally had is going to reduce, like it did here, down to polynomial terms. So it's not uncommon to see linear combination of polynomial terms being solutions to Cauchy-Euler differential equations. All right. What we'd like to do now is, before we get into some more examples, we'd like to show that how this is going to work in general. As you guys can see, when we got to that second derivative here, the second derivative of y with respect to x was not the same as the second derivative of y with respect to z. It actually turned out to be the second derivative with respect to z minus the first derivative with respect to z. So we're going to have to be careful about how we do these higher order substitutions. So we're going to prove a little theorem that says how those substitutions work at any order. So let's go ahead and take a look at that theorem, and then we'll be able to talk about some more examples. So for this theorem, we're going to let y be a smooth function of x. What a smooth function basically means is that it has enough derivatives so that all the derivatives in this theorem actually make sense and are well defined. You can just think about it as being smooth as a slightly lesser condition than being infinitely differentiable. We're just saying it has enough derivatives to do whatever we'd like it to do. And we're going to let the substitution be x equals e to the z. Then we're claiming that the following relation holds for all whole values of k. Namely that x to the k times the kth derivative of y with respect to x is equivalent to this expansion, d times d minus 1 times d minus k minus 1 of y, where d represents the derivative now with respect to z. Okay, now, in a moment, we're going to sort of prove this, but I would like to just sort of state how in general this is going to help us. So note the pattern here will be that things like x dy dx will be equivalent to d of y, whereas x squared times the second derivative, x squared times the second derivative is going to be d minus 1 of y. Or as we found in the first example where we sort of motivated this, d squared minus d. If you have x cubed times the third derivative of y with respect to x, then it would be d minus 1, d minus 2 of y, and so on. So you can sort of see how this pattern is going to make it very easy for us to convert from something that is in Cauchy-Euler form, some linear combination of things like this, into something that is going to be in constant coefficient form. Now, of course, we need to prove this, but I just wanted you guys to sort of see what the result of this is. Because in sort of condensed notation, it might not be immediately clear how much faster this is going to make things. But if you notice this pattern and you think about how it would expand on, it's going to make it very easy to do this sort of substitution. So let's do this proof. To actually prove this, we're going to do it as a proof by induction. So we're going to do a proof by induction. So the base case will be with k equals 1, which means that we need to show that x dy dx is equal to d of y. And again, where d of y means the derivative of y with respect to z. Now, if you think about that, that's actually what we did back right over here. That's exactly what we did right there. So we've already shown this. So, already proved this. Okay. So the base case was actually the first part we did. We actually proved two base cases if we really wanted to. We did the base case for k equals 1 and for k equals 2. That's because we didn't know we were going to have this general theorem just yet when we did our first example. But actually, we've already shown this for k equals 1 and k equals 2. To do a true proof by induction, we just need it for k equals 1 here. So I'm not going to even mention the k equals 2, but, well, we've already got this k equals 1 here. All right, now we're going to assume that for some k equals n, right, x to the nth derivative of y with respect to x is d minus 1 down to d minus n minus 1 of y. And what do we need to show? We need to show that this will hold for the next step. We need to show, in other words, that this will hold for x to the n plus 1, n plus first derivative of y with respect to x is going to be d minus 1, d minus n minus, oh, forgot my dots there, dot 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 d minus n minus 1, and then d minus n of y. Okay, that's what we need to show. So let's start from sort of one side and see if we can work to the other. Now, it might not be immediately clear how we're going to actually even get to this. But if you think about it, this expression here involves the n plus first derivative. So it might be a good idea to start with something that involves the nth derivative. So let's start with our inductive hypothesis. So start with the inductive hypothesis. So we're going to start with the assumption that x to the n, dny dxn is d minus 1, d minus n minus 1 of y. Okay, what I'm going to do then is I'm going to differentiate both sides with respect to x. So differentiate with respect to x. Okay, on this left-hand side, it's going to be a product rule. First part of the product rule should be very easy. We're going to get nx to the n minus 1, dny dxn, plus then xn. Then we take the derivative with respect to x of this, and of course that gives us dn plus 1y over dxn plus 1. Okay, now, going to be a bit messier to apply the derivative with respect to x over here. Because remember, this is all derivatives with respect to z of y. But we know how this works. We know that what's going to happen is we're going to get another derivative with respect to z times the derivative of z with respect to x. Because what is that? That's chain rule. So when we apply the derivative here, what we're going to do is we're going to get d of all this stuff, d minus 1, d minus n minus 1 of y. So that's another derivative with respect to z. And then we're going to get times dz dx, right? That's chain rule. Take a derivative of y with respect to z, and then the derivative of z with respect to x. So let's clean that up a little bit. What is the derivative of z with respect to x? Well, remember, we're doing that substitution. X equals e to the z, or z equals ln x. So this is 1 over x. So we've got nx n minus 1, dny dxn, plus xn dn plus 1y over dx to the n plus 1 equals d minus 1, d minus n minus 1 of y, then times 1 over x. Now, just to be clear, could I actually just put this guy in here and call it d squared? Sure, definitely could. Not actually useful for the proof, but certainly do keep in mind this extra set of parentheses is not necessary. This d could go right into this guy and make that a d squared there. Just not useful for sort of seeing the proof, but it would be technically valid. Okay, well, let's go ahead then and multiply on both sides by x to get rid of this 1 over x there. So notice that that then becomes nx to the n dny dxn plus x to the n plus 1 dn plus 1y over dxn plus 1 equals d minus 1 down to d minus n minus 1 of y. Okay, now notice that this is starting to look good, right? Because we need to show something about x to the n plus 1 times the n plus 1 derivative, and that's what we have right here. This looks a little bit odd, but let's move this onto the other side. So let's go ahead and do that. So if we do that, then we would get x to the n plus 1 dn plus 1y over dxn plus 1 is equal to d of d minus 1 d minus n minus 1 of y, and then minus nxn dny dxn. Okay, now actually, this is a sort of interesting proof by induction because we're going to use the inductive hypothesis twice. We use the inductive hypothesis to start off with this relation. But actually notice that this right here is x to the n times the nth derivative of y with respect to x. So we can replace this with this expression right here. Now we'll do that on the next page to make it a little less messy. So let's grab what we have right here. Okay. Copy that. We'll move that on to next page. Oh. Didn't quite copy that correctly. There we go. Okay. All right. So we're right there. But now, like we said, we're going to go ahead and we're going to replace this guy with the inductive hypothesis, which said that this should be equal to d minus 1 down to d minus n minus 1 of y. So let's go ahead and do that. So this tells us that xn plus 1 dn plus 1y over dxn plus 1 is d of d minus 1 d minus n minus 1 of y minus n then times this guy, which we said would be d minus 1 down to d minus n minus 1 of y. Okay, now we're basically there. Notice that this and this right here, those are identical. So this guy and this are identical. So we can factor this out in front. What is that going to leave us then with? D minus n. So if we do that, we get x to the n plus 1, dn plus 1y, dxn plus 1 is going to be d minus 1, d minus n minus 1. So we factor all that stuff out. What's left then? D minus n. So we get times d minus n, all of y. And what do you know? That's exactly what we wanted to show. Check. So we proved that this is going to hold in general. So we've just shown via a proof by induction that this relation is going to hold whenever you do this substitution, which basically means, as we said here, you're going to have this summary, right? X dy dx can be thought about as d of y. X squared dy dx is going to be d minus 1 of y. X cubed, d minus 1, d minus 2. If you add x to the fourth, and the fourth derivative of y with respect to x, then you'd have something that would involve d minus 1, d minus 2, and d minus 3, so on and so forth. This will hold for any whole value of k. Now, it should be clear, I'm not going to prove it. I believe your book actually puts it into a separate theorem, but they claim that if you have this substitution then what's going to result is a constant coefficient differential equation. But I hope that's obvious because obviously all these just involve constant coefficients. So it should be clear that using this substitution on a Cauchy-Euler is always going to result in a constant coefficient. Now, this video has already gone on a little bit. I was initially going to go jump into the examples right away, but we'll actually put the examples of solving these Cauchy-Eulers into the next video here.